In a previous lesson, we saw that pumps convert the mechanical energy of a turning shaft into hydraulic energy in the form of pressure and flow. This pressure and flow can be converted into linear mechanical force by cylinders which apply force in a straight line to extend or retract a cylinder rod. In this lesson, we will see how pressure and flow are converted into rotary mechanical force by hydraulic motors. We will also see how the efficiency of motors can be changed, so the force they develop can match the work being done as closely as possible. Three types of motors are commonly used in industrial hydraulic systems: the vane motor, the gear motor, and the piston motor. While each of these motors looks similar to its counterpart pump, each operates on a principle exactly opposite of the pump. That is, hydraulic motors take fluid under pressure, apply it to the surface area of an internal moving part to create a rotary force, and then return the fluid to tank. When operating any motor, two main factors must be considered: torque and speed. Torque is the rotary force applied to the shaft, usually expressed in pound-inches. Speed is the rate at which the shaft turns, usually expressed in revolutions per minute. Let's look at a vane motor to see how pressure and flow in a hydraulic system affect the motor's torque and speed. Like the vane pump, the vane motor has a rotating group with vanes that ride along an offset cam ring. Fluid moves in and out of the motor through port plates. As system pressure rises, the force applied to the vane increases, and the rotary force developed at the shaft, the torque, also increases. As long as the size of the motor remains the same, increasing the pressure will increase the torque. If pressure drops, torque drops. A similar relationship exists between flow rate and speed. If flow through the motor increases, then the vanes will turn faster, and the speed of the shaft will increase. Again, this direct relationship between flow rate and speed is the same for all hydraulic motors. Increasing the flow rate will increase the speed, and decreasing the flow will decrease the speed, as long as the size of the motor remains the same. The size of a motor means its displacement, or how much fluid it can hold. In a vane-type motor, changing the displacement can only be done by changing the cartridge assembly, which is the rotating group and the cam ring sandwiched between the port plates. Increasing the size of the cartridge assembly without changing the pressure will increase the torque, because the vanes of the larger cartridge assembly have more area exposed to pressure. Decreasing the size of the cartridge assembly without changing the pressure will decrease the torque, because the vanes in the smaller assembly will have less area exposed to pressure. Increasing the displacement without changing the flow rate will slow the motor down, because the same amount of fluid has to fill a larger space inside the motor. And decreasing the displacement without changing the flow rate will speed the motor up, because the same amount of fluid only has to fill a smaller space inside the motor. Now, let's take a close look at how each type of motor works. In a vane motor, the motor won't turn until there is a seal between the vane and the cam ring. That means that centrifugal force cannot be used to force the vanes out to the cam ring at startup. In some vane motors, springs are used to hold the vane against the cam ring. This can be done with a coil spring or with a spring attached to a post. In either case, once the motor is turning, fluid pressure is directed to the underside of the vane to help maintain a tight seal. Fluid pressure may also be used to force the vane out before the motor starts. This is done by using a check valve, which prevents fluid from entering the motor inlet until pressure is high enough to force the vane out against the cam ring. Gear-type hydraulic motors operate in a way that is similar to vane-type motors, except pressure at the motor inlet pushes against the sides of the gear teeth, forcing them to rotate. A tight seal between the gears and the housing minimizes fluid leakage past the teeth. The torque created at the motor shaft depends on the pressure at the motor inlet and on the exposed tooth area. The greater the pressure, the greater the torque, and the more exposed tooth area, the greater the torque. The movement of the gears in the gerotor motor is similar to the gerotor pump. Pressurized fluid enters the port plate, pushing on one side of one tooth of both the inner and the outer gear. Since fluid on the outlet side is allowed to exit through the outlet port, there is very little pressure to oppose the gear movement, and both gears rotate. The torque developed is based on how much pressure there is at the inlet port and on the size of the gears. The higher the fluid pressure, the greater the torque at the motor shaft, and the larger the teeth, the greater the displacement and the greater the torque. In a piston motor, fluid pressure pushes against the pistons. The piston shoes are forced to slide up and around the swash plate, turning the cylinder barrel as they move. After each piston passes the top of the swash plate, it starts back down, forcing fluid out of the piston bore and through the outlet port as the shoe and piston ride back down the swash plate. Increasing the pressure forces the piston shoes more firmly against the swash plate, increasing the torque applied to the cylinder barrel and to the shaft. Unlike vane motors and gear motors, piston motors can be reversed without changing the direction of flow through the motor. This type of motor is called an over-center piston motor because all that's needed to reverse the direction of rotation of the shaft is to tilt the swash plate past or over its center. As the swash plate is tilted toward vertical, the motor displaces less and less fluid. Usually, to reverse direction, the motor is stopped. When the motor is restarted with the swash plate tilted over center, the piston shoes, which had been rotating in one direction, go back the other way, turning the cylinder barrel in the opposite direction and reversing the direction of the motor shaft.